This little video we're going to review logarithmic and exponential functions. And again, this is a review, but it's good to be reminded of some of the things that we learned in previous math courses. Let's start with exponential functions. So maybe we'll start with just doing the law of some of the exponent laws. So you would know this one. If we had a to the power of n, then that's really a times a times a n times. So I don't know how many there would be here, but you would multiply a by itself n times. So for instance, 3 to the power of 5, of course, 3 times 3 times 3 times 3 times 3. Other exponent laws that you've learned is, remember, if the exponent is negative, that means we take the reciprocal of the base. So instead of a to the power of negative n, I can write this as 1 over a to the power of positive n. So a negative exponent, remember, means take the reciprocal of the base. You also learned some exponent laws like this. If we had some fractions, a to the power of p over q, then that becomes the q root of a all to the power of p. So the denominator is your root and the numerator is your exponent. So if we had 8 to the power of 2/3, what this really means is that this is the cube root of 8 all squared. So the third root of 8 is 2, and 2 to the power of 2, or 2 squared, is 4. And then the other one we had was anything to the power of 0 is equal to 1. So that's a review, again, of some of your exponent laws. Now let's look at the graph of some of these exponential functions. So let's look at the graph of, say, y equals 2 to the power of x. Well, we could make a table of values here. We could look at some x values. Let's just pick those. So if x is 2, 2 to the power of 2 is 4. If x is 1, 2 to the power of 1 is 1. If x is 0, remember from our exponent laws, 2 to the power of 0 is 1. Oh, sorry, 2 to the power of 1 is 2 here. So let's try that again. 2 squared is 4. 2 to the power of 1 is 2. 2 to the power of 0 is 1. There we go. 2 to the power of negative 1. Remember, the negative exponent means take the reciprocal of the base, so that's like a half to the power of 1. So that would be 1/2. And 2 to the power of negative 2 is the same thing as 1/2 to the power of positive 2. Negative exponent, reciprocal of the base. 1/2 squared is 1/4. So when x is minus 2, this y value was 1/4, negative 1 was 1/2, 0 was 1, 1 was 2, 2 was 4. And so our exponential functions would look something like this. If we looked at the graph of y equals 1/2 x, and we did a table of values, we'll do the same ones. So here when x is 2, 1/2 times 1/2 is 1/4. 1/2 to the power 1 is 1/2. 1/2 to the power of 0 is 1. 1/2 to the power of negative 1. Negative means flip the base. So the reciprocal of that is 2. 2 to the power of 1 is 2. And so 1/2 to the power of negative 2 would be 2 to the power of 2, which is 4. So here, negative 2 becomes 4. Negative 1 becomes 2. 0 becomes 1. 1 becomes 1/2. And 2 becomes 1/4. And so we get a graph looking like this, which, as it turns out, is the same graph as the red one, except it's been reflected in the y-axis. Now when we look at these two graphs, the blue one and the red one, we can see that they're actually the same image reflected in the y-axis. You remember back to your transformations that we reflect graphs in the y-axis by replacing x with minus x. So if I took Let me get my red one here again so the colors aren't confusing. So if we took this red function, which is y equals 2 to the x, that's this one here, and we replace the x with minus x, then that should be a reflection in the y-axis. Well, we know that a negative exponent means the reciprocal of the base, so that would give us this function with a positive exponent, which is the one we graphed over here. So those are some graphs of some exponential functions. Now, if we took these points here and took the inverse of them, so I've got a picture, I'll just put these points on here again. So this is the point, whoops, I want red. This is the point 2, 4, this is the point 1, 2, this is the point 0, 1, this is the point negative 1/2, and this is the point negative 2, 1/4. So this is the graph of y equals 2 to the x, the same one we did the last time. If we took the inverse of this function, so if we swap the x, y values around, so now if I go 1/4, I'm going to go negative 2. So that would give us a point right here. Negative 1/2 becomes a half negative 1. 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. 2, 4 becomes 1, 2, 3, 4, 1, 2. We would get a graph that looks like this, which, of course, because it's an inverse, is the graph that's reflected in the line y equals x. And you can see they're mirror images of each other. And we learned that the inverse of an exponential function is a logarithmic function. So y equals log base 2 of x would be the inverse of the function y equals 2 to the power x. So let's just review some of the things that we learned about logarithms. So the short answer to what a logarithm is an exponent. So if the question is, what is log base 2 of 8? What we're really asking is, what's the exponent that you'd have to put on 2 to make it equal 8? And of course, 2 to the power 3 equals 8. So log base 2 of 8 is 3. And we know that we could have base 10 logarithms, and usually if we have base 10 logarithms, we don't actually write the number 10 down there because we use those a fair bit. So log 100 is really the same thing as log base 10 of 100, and so we'd be asking ourselves, what's the exponent on 10 that would give us 100? Log 100 would be 2. Now there's one other base. I mentioned that we use this a fair bit. There's one other base that we use a lot, and that's base e. And the number e is an irrational number, and it's approximately 2.718. So e is approximately 2.718. It's an irrational number, and you'll see later on in this course why it's so popular to use in calculus. So we could do log base e of functions as well. We could do log base e of 7, and that would be like asking, what's the exponent on this irrational number that equals 7? Well, we use log base e so often that we've abbreviated log base e as ln for the natural logarithm. So when you see ln 7, that really just means what is log base e of 7. So we'll be using ln, and we'll be using e a lot when we're working with our exponential and logarithmic functions. And I'll show you a few examples of those a little bit later in this video. We also did a whole pile of log rules, and so it's good to remember those. Log of a times b, remember, is the same thing as log a plus log b. Remember that rule. Log of a divided by b is the same thing as log a minus log b. Log of a to the power of n. If you have an exponent Exponent can be brought down in front, so that's n times log a. And then we had a couple other ones that we would use. One would be a change of base rule. So if we have log base a of b, we can write that as log base n of b divided by log base n of a. So log b divided by log a, and we can make that whatever base we want. So for instance, if we wanted to do this in the calculator, log base 2 of 3, we don't have base 2 in the calculator, but we have base 10, so we could go log 3 divided by log 2. So just putting this in the calculator, we could go log 2 divided by log 3. Oops, sorry, log 3 divided by log 2. Log 3 divided by log 2. So the exponent should be 1.58 approximately. So 2 to the power 1.58 is 3. The only other logarithm that we have on here is, so here's the log button, is right beside it you see is ln, which is log base e. So instead of figuring out log base 2 of 3 by going to base 10 logarithms, I could also say, okay, well that's log base e of 3 divided by log base e of 2. And of course, when we go to the calculator and punch ln3 divided by ln2, we're going to get the exact same answer there, 1.58. As I should use squiggles here because it's approximately 1.58. Right, and there's one other kind of expression that we use often in logarithms. If you have an equation, log base a of b equals c, then that's equivalent to saying b equals a to the power of c. For example, let's go back to this one that we did before. Log base 2 of 8 equals 3, because the exponent on 2 to give you 8 is equal to 3. That's like saying 8 is equal to 2 cubed. 8 equals 2 cubed. So here's the expression written as a logarithm. Here's that same expression written as an exponent. So this is the relationship between logarithms and exponents, and we know that they're inverses of each other. So here we'll do a couple of questions where we're solving for the exponent. Those are the variables in exponent here. So this is an exponential function because the variable's an exponent. Here's another one. And anytime we're solving for x and x is an exponent, we must take the logarithm of both sides. So on this one, we could take log base 10 of both sides. So I'm going to take the log of this side, and that'll equal the log of this side. So this has an exponent. I can bring that down in front. So x log 3 equals log 2. And then finally, we'll divide both sides by log 3. And we'll get x is equal to log 2 divided by log 3, which, using our exponent laws, or our logarithm laws, is the same thing as log base 3 of 2. That's log 2 divided by log 3. So there's one example of solving an equation. Here's another one. Now this one has a base e in it. So this one would make more sense to take the natural log of both sides. So I'd have ln of this side equals ln of that side. Now here we have log of a times b. So our log rule says that should be log a plus log b. And then this second term here has an exponent, so I can bring that down in front. And now I'm going to try to isolate x. So I'm going to minus ln6 from both sides. And that gives us this. And now here I've got ln e. Well, you remember this. If I asked you this question, what's log base 3 of 9? You'd be saying, well, what's the exponent on 3 that gives you 9? That's 2. And if I said, okay, what's log base 9 of 9? You should tell me that's 1, because the exponent on 9 needs to be a 1 in order to produce 9. So if I say, what's ln e equal to? You know that ln really just means log base e of e. So this question is saying, what's the exponent on e that's going to give you e? Well, that's just 1. So ln e, of course, will just be 1. So this is just 2x equals ln 5 minus ln 6, and so to isolate x, we can divide by 2. And we have x equals ln 5 minus ln 6 divided by 2. So there's how we can, just a review of some questions solving exponential equations. Let's look at solving a couple of log equations. Okay, looking at a couple of log equations here. Log base 3 of x, 2 plus x equals 2. And over here I have another log equation, this one in base e, ln 4x minus 3 times ln x squared equals ln 2. So on this first one here, I've got logs only on one side of the equation. So remember this. If we have log base a of b equals c, I call it the back rule. If you have log base a of b equals c, that means b equals a to the c, which spells back kind of when you look at it. So when you write it as ABC, log base a of b equals c, writing it as an exponent, b equals a to the power of c. So that's what I'm going to use here. I've got log base a of b equals c. That means that b equals a to the power of c. So 2 minus x equals 3 squared, which is 9. I'll minus 2 from both sides to get negative x equals 7. And now I'll divide by negative 1 to get x is negative 7. Oh, so I did something wrong here. It's like something's not right. That's because I wrote the question down wrong. Let's try that again. Log base a of b equals c. b equals a to the power of c. So it's 2 plus x I had. So 2 plus x equals 3 squared. 2 plus x equals 9. And now I'll just minus 2 from both sides to get x equals 7. So the solution to this equation is x equals 7. Now remember, whenever we're solving a log equation, what we take the log of, so we had log base a of b, the b has to be greater than 0. Remember, we can only take logs of numbers that are positive. So I just want to double check that when we put 7 in here, that 2 plus 7 is going to be greater than 0. It is. 2 plus 7 is 9, and log base 3 of 9 is indeed 2. Let's check this next one out. This one has logs on both sides of the equation. So on this question, we're going to use the strategy that if we have log a equal to log b, so if I can get a single logarithm on this side and make it equal to the single logarithm on this side, then I can just say, okay, if log a equals log b, then it makes sense that a must equal b. So we'll get a single log on the left side here, so ln of 4x. Ooh, this has a number in front. I can move that up and make an exponent. Oops. So brought the 3 up on an exponent. Now x squared cubed, our exponent laws said we should multiply those exponents. So x squared cubed would be the same thing as x to the power of 6. Power of a power rule times the exponents. And now I have log a minus log b. So I can combine those together to get a divided by b. And now I'm at this situation where I have log a equals log b. So I can say, okay, then it must be logical to assume then that this is equal to this. And now I'm going to multiply both sides by x6, which gives me this. And then I will set the equation equal to 0 by bringing this over to this side. And now I can factor out a common factor of 2x. And I can solve my well, it's not a quadratic. I could solve my binomial here. This times this equals 0. So the first term can equal 0. And the second term can equal 0. Dividing by 2 gives me x equals 0. Here, bringing the 2 to the other side, And now taking the fifth root to isolate x gives me the fifth root of 2. So I've got two answers here, 0 and fifth root of 2, and I'm just going to double check. If I go back and put 0 in here, in my original question I got the natural logarithm of 0. I can't take the log of 0, so this one cannot exist. The fifth root of 2, if I multiply that by 4, that's positive, that's okay. If I take the fifth root of 2 and I square it, that's going to be okay. So my only solution would be x equals the fifth root of 2. So there's some review again of exponential and log functions and equations.